All right, let's dive straight into the fascinating world of microscopic precision. Today, we're unpacking a literal game changer for engineers and makers, the micrometer screw gauge. Imagine holding a single hair-thin copper wire in your hand. How in the world do you measure its diameter accurately? I mean, a standard ruler? Completely useless. You can't just line it up against those millimeter marks and hope for the best. We need something engineered specifically for the microscopic level. So here's our roadmap for this explainer. First, the precision problem. Then, the anatomy of the micrometer. Next, we'll hit the math of precision, followed by beware the zero error, and finally, actually measuring a thin wire. Let's start with Section 1, the precision problem, finding the right tool for the job. Look at the limitations of our everyday tools. A measuring tape or a meter rule, they bottom out at a least count of just 1 millimeter. Vernier calipers get us down to 0.1 millimeters, which is better, sure, but still not enough for our thin wire. But our hero today, the micrometer screw gauge, it boasts a least count of an astonishing 0.01 millimeters. I mean, that is a microscopic fraction. Moving right along to Section 2, anatomy of the micrometer, breaking down the mechanical components. So, a micrometer isn't just some basic clamp, it's a super precise instrument. The object you're measuring, like our thin wire, goes right between the static anvil on the left and the moving spindle on the right. And the rest of the gang, the sleeve, the thimble, and the ratchet, they all work in total harmony to move that spindle and lock in your highly accurate reading. Now, the way this movement actually happens is kind of brilliant. The sleeve is the stationary barrel holding the main scale, with markings every half a millimeter. And around that sleeve, you've got the rotating thimble, which has a circular scale divided into exactly 50 parts. So turning the thimble literally pushes the spindle forward or backward. It perfectly bridges the gap between a simple twisting motion and a highly precise linear measurement. And I absolutely love this next detail. Sitting right at the end of the tool, the ratchet acts as a built-in mechanical safeguard. It prevents over-tightening by giving you this distinct, satisfying click when the micrometer is ready to be read. It ensures you don't accidentally crush whatever delicate thing you're measuring, which, would totally ruin your accuracy. Let's look at Section 3, the math of precision. Calculating the least count. Okay, so it all starts with this concept called the pitch. The pitch is simply the distance the spindle moves on the main scale when you give the thimble one full 360-degree spin. In a standard micrometer, that distance is exactly 0.5 millimeters. One full spin equals half a millimeter forward. Now we take that pitch to figure out our least count. And remember, the least count is literally the absolute smallest measurement we can trust this tool to give us. We calculate it by taking that pitch and dividing it by the total number of divisions on that rotating circular scale. Let's do the math. We take our 0.5 millimeter pitch, divide it by the 50 divisions on the thimble, and boom! The result is a staggering 0.01 millimeters of precision. Every single tiny tick mark you rotate advances the spindle by exactly 1/100th of a millimeter. There is simply no way you could do that with a standard ruler. Section 4. Beware the zero error, calibrating before you calculate. Now, before you measure anything, you absolutely have to make sure your instrument is calibrated. You do this by closing the anvil and spindle entirely, with absolutely nothing in between them. When they touch, the zero mark on the circular scale has to perfectly align with the horizontal reference line on the main scale. If they match up perfectly, great, no zero error, and you're officially ready to measure. But if they don't align, well, you've got a zero error, and you'll need to correct it. It's a quick visual check. If the zero on the circular scale sits below the horizontal line, that's a positive error, meaning the tool has a bit of a head start and is reading too high, so you'll need to subtract that from your final number. If the zero is above the line, it's lagging behind, reading too low, so you add that error back in. It's a super simple adjustment, but absolutely crucial for accuracy. Finally, Section 5, measuring a thin wire, putting the process into practice. All right, let's actually run through the physical process. Think of it like a recipe. First, carefully place your wire between the anvil and the spindle. Second, gently turn the thimble to close the gap. Third, and this is the critical part, use the ratchet at the end and stop turning the exact second you hear that click. That click is everything. It means the pressure is perfect. Finally, lock it in and read the measurements on both scales. Once your wire is clamped perfectly, you just plug your two scale readings into this really elegant formula. The total thickness simply equals your main scale reading plus the circular scale reading multiplied by our trusty least count. Let's look at a real-world example here. Say we read the main scale and it shows exactly 0.5 millimeters. Then we check the circular scale and see that line 25 lines up perfectly. So the calculation is 0.5 millimeters plus 25 times our least count of 0.01. That gives us 0.5 plus 0.25, meaning our final hyper-accurate measurement for this wire, which is basically the thickness of an acoustic guitar string, is exactly 0.75 millimeters. We started with a tiny wire